An apple and a moment of genius. In 1687, an apple fell on Sir Isaac Newton's head, and that moment changed the world forever. It led to the development of the most successful theory of gravity ever created. His law of universal gravitation was so elegant and so powerful that it explained not only why apples fall from trees, but also why planets orbit the sun and the moon causes the tides. We take this law for granted today, but until Newton, no one had ever figured out why these things happen. But now it is time for a paradigm shift because we are about to find out what's wrong with Newton's theory and how Einstein turned it into a new and improved version. This is the story of gravity. Part 2. Newton's apple fell when he was sitting under an apple tree and thinking about the universe. He was wondering why it was that objects like the apple had a tendency to fall towards the center of the earth. Well, according to Aristotle, who was the leading scientist of his time, heavy objects fall because they are made of some invisible material called earth. This stuff makes them slow and sluggish, and it wants to return to the center of the earth because that's where it came from. But if you think about it, that's really stupid because it would mean that if you took a rock into space, it would suddenly start floating around aimlessly because there's no earth element in space to make it fall back to the center of the earth. Not to mention that it doesn't explain why the moon stays in orbit around the earth instead of falling to the ground. And it definitely doesn't explain why Mercury orbits the sun without falling into the solar abyss. So even though everyone believed Aristotle was right, Newton knew that there had to be something else going on. Then one day, while he was taking a break from thinking about the universe and contemplating the existence of God, an apple fell on his head. That was the moment of genius. Newton realized that there must be a force of nature that pulls objects towards each other. He called this the law of universal gravitation. It says that every object in the universe attracts every other object with a force that depends on their masses and the distance between them. The closer they are, the stronger the force. If an apple falls from a tree, it's because the earth is pulling it towards the ground. But if you were to take the apple with you into space, it would still be pulled towards the earth. Because the earth is big, its gravitational pull is strong enough to overcome the inertia of the apple. Inertia is the tendency of an object to resist changes to its motion. If there were no forces acting on the apple, it would keep floating in the same direction at the same speed forever. But the bigger the mass of the object you are close to, the harder it is to overcome its gravitational pull. Eventually, the apple would get so close to the earth that its inertia wouldn't be enough to keep it from being pulled all the way down. So it would fall to the ground. The same thing happens with Mercury. The sun's gravitational pull is so strong that it keeps the planet in orbit around it. But if Mercury were to get too close to the sun, the gravitational pull would become so strong that it would tear the planet apart. Newton's theory was incredibly successful. It could explain not only why apples fall from trees, but also why the moon causes the tides and why galaxies spin. It even predicted things that hadn't been observed yet, like the fact that light bends around massive objects. Scientists believe that this law would never be disproven. It was the final word on gravity. Fast forward a couple hundred years, and we now know that Newton's theory has some major problems. It doesn't work very well at explaining gravity at very large distances or very small ones. The GPS system, for example, relies on extremely accurate measurements of time and distance. These measurements are based on Einstein's theories of special and general relativity. For example, the GPS satellites have to take into account the fact that time passes slightly slower for them than it does for us on the ground, because they are further away from the Earth and therefore further away from the gravitational field. If they didn't do this, they would slowly drift out of position and eventually be completely useless. Even though Einstein's theories are more accurate, we often use Newton's theory instead because it is much easier to work with and gives nearly identical results in most cases. It's kind of like using the speed limit as an example. We know that the actual speed limit can change depending on the weather conditions and how many other cars are on the road, but we just use the posted speed limit because it's easier. So what are the circumstances where Newton's theory fails? One of those circumstances is when you have two very massive objects very close to each other. For example, when two neutron stars orbit each other, the gravitational waves they emit cause the orbit to decay, and eventually the two stars collide. At this point, Newton's theory of gravity can't tell us anything about what happens because it breaks down at this scale. Another circumstance where Newton's theory fails is when you have a single very massive object and something very small. For example, if you want to measure the gravitational field of a black hole, then you need to use Einstein's theory of general relativity because otherwise you will end up with infinities. Also, if you want to measure the gravitational field of a planet, then you need to use Einstein's theory because otherwise you'll get the wrong answer. If you use Newton's theory, you'll get an answer that's off by 3%. This might not seem like a lot, but it's enough to mess up your day if you read the one who's late to work because the planet's gravitational pull is 3% stronger than predicted by Newton's theory. It's not much of an error, but it's still an error nonetheless. And it turns out that this isn't the only way in which Newton's theory is off. When measuring really big things like galaxies, Newton's theory also breaks down because the amount of matter in the universe isn't evenly distributed. This means that the gravitational pull of galaxies isn't always in the direction you would expect. You can see this effect when looking at spiral galaxies. The stars in the middle of the galaxy move faster than expected. This is because the visible matter in the middle of the galaxy isn't the only thing that's affecting the gravitational pull. There must also be some invisible stuff in the middle of the galaxy that's making the stars move faster. We call this stuff dark matter. Dark matter doesn't interact with normal matter, so we can't see it directly. We can only observe its effects indirectly through gravitational lensing and by measuring the motion of stars in galaxies. We think that there's about 5 times more dark matter in the universe than normal matter. But since it doesn't interact with normal matter, we don't know exactly what it's made of. Some scientists think it's made of exotic particles that we haven't discovered yet. Others think it's not real at all and that Newton's theory of gravity needs to be modified at large distances. This idea is controversial, but if it's true, then it would revolutionize our understanding of the universe because it would mean that there are some things in the universe that we don't know about yet. And that's the problem with Newtonian gravity. It's not a complete theory. It's a good approximation of reality, but it's not perfect. Einstein's theories of special and general relativity are more accurate, but they're also more complicated. And in most cases, we can get away with using Newton's theory. It's like when you're driving a car, you don't need to worry about the speed limit being absolute. You just drive safely and obey the posted speed limit. And that's what scientists do when they're studying gravity. They use Newton's theory because it's easier and it works in most cases. But every once in a while, they need to use Einstein's theories because Newton's theory just isn't accurate enough. Thanks for watching.